ನಮಸ್ತೆ ಸರ್. ಮಕ್ಕಳು ಜಾಯ್ನ್ ಆಗ್ತಾ ಇದಾರೆ. ನಾವು ನಿಮ್ಮ ಬಗ್ಗೆ ಒಂದು ಸ್ಮಾಲ್ ಇಂಟ್ರೊಡಕ್ಷನ್ ಕೊಟ್ಕೊಂಡು ಶುರು ಮಾಡೋಣ ಸರ್.
ಸರಿ ಸರ್.
ಇಂದಿನ ಉಪನ್ಯಾಸ ಕಾರ್ಯಕ್ರಮ ಮಾಲೆಯಲ್ಲಿ ಡಾಕ್ಟರ್ ಚಂದ್ರಶೇಖರ್ ಶೆಟ್ಟಿ ಸರ್ ಅವರನ್ನು ಸ್ವಾಗತಿಸುತ್ತಾ ಸೆಮಿಕಂಡಕ್ಟರ್ ವಿಷಯದ ಮೇಲೆ ಉಪನ್ಯಾಸ ನೀಡಲಿದ್ದಾರೆ. ಅದೇ ರೀತಿ ನಮ್ಮ ಅಕಾಡೆಮಿ ಅಧ್ಯಕ್ಷರಾದಂತಹ ಅಯ್ಯಪ್ಪನ್ ಸರ್ ಅವರನ್ನು ಸ್ವಾಗತಿಸುತ್ತಾ ಹಾಗೂ ನಮ್ಮ ಅಕಾಡೆಮಿಯ ಮುಖ್ಯ ಕಾರ್ಯನಿರ್ವಹಣಾಧಿಕಾರಿಯಾದಂತಹ ಡಾಕ್ಟರ್ ಎಂ ರೇವಶ್ ಅವರನ್ನು ಕೂಡ ಸ್ವಾಗತಿಸುತ್ತಾ ಈ ನಮ್ಮ ಚಂದ್ರಶೇಖರ್ ಶೆಟ್ಟಿ ಸರ್ ಬಗ್ಗೆ ಒಂದು ಕಿರು ಪರಿಚಯ. Sir completed his MSc Physics and also has MPhil in Physics and PG Diploma in Computer Applications and one more Bachelor of Education B.Ed and one more MSc in Information Technology, and also I passed in KSET and having PhD from Mangalore University on non-linear optical materials. And presently, sir working as head of the department of PG students and research in physics and research coordinator for DST FST program. Also mentor DST Inspire program, Government of India. And also have some teaching experience and academic responsibilities by teaching in the department of MSc Physics at St. Elias College, Mangalore from July 2012. Joined as a lecturer in the Department of Physical Electronics at St. Elias College, Mangalore, 10th July 1998. Also, sir was selected as some summer research fellowship, selected as a summer research fellowship by Indian Science Academy of Sciences and worked on the topic of EPR studies of magnets at the Department of Physics, Indian Institute of Science, Bengaluru during May-July 2018. And selected for summer research fellowship by Indian Academy of Sciences and worked on the topic determination of the elastic constants of a pneumatic liquid crystal using radiogenic effect of Raman Research Institution, Bangalore during May-June 2013. And sir published many papers, like 70 research papers, which include the following journals like Material Letters, Optical Materials, Journal of Applied Physics B, Beta, Optic International Journal for Light and Electronic Optics, Journal of Molecular Structure, Results in Physics, Journal of Optics and Laser Technology, Materials Today, Proceedings, Journal of Materials Technology, Journal of Material Research Innovations. And sir presented some 14 international research papers, and also some having external curricular activities, like worked as a activity NCC officers in Army Wing of NCC in the rank of Lieutenant from July 2005 to July 2009. Okay, thank you, sir. Over to you.
ಎಲ್ಲರಿಗೂ ನಮಸ್ಕಾರ. ಪರಿಚಯ ಮಾಡಿದ KST ಪದಾಧಿಕಾರಿಗಳಿಗೆ ವಂದನೆಗಳು. ಅದೇ ರೀತಿ ಈ ಅವಕಾಶ ಕಲ್ಪಿಸಿಕೊಟ್ಟ KST ಅಧ್ಯಕ್ಷರಾದ ಅಯ್ಯಪ್ಪನ್, ಕಾರ್ಯನಿರ್ವಾಹಕರಾದ ರಮೇಶ್ ಸರ್, ಎಲ್ಲರಿಗೂ ನಮಿಸುತ್ತಾ ಇವತ್ತು ಸೆಮಿಕಂಡಕ್ಟರ್ಸ್ ಬಗ್ಗೆ ಸ್ವಲ್ಪ ತಿಳಿದುಕೊಳ್ಳುವ ಪ್ರಯತ್ನ ಮಾಡುವ. ನಿಮಗೆಲ್ಲ ಗೊತ್ತಿದ್ದಾಗೆ ಸೆಮಿಕಂಡಕ್ಟರ್ಸ್ ಈ ಶತಮಾನ ಮತ್ತು ಕಳೆದ ಶತಮಾನದಲ್ಲಿ ಬಹಳ ಪ್ರಮುಖವಾಗಿ ಪ್ರಭಾವ ಬೀರಿದಂಥ ಒಂದು ವಿಜ್ಞಾನದ ತಂತ್ರಜ್ಞಾನದ ಒಂದು ವಸ್ತು ಸೆಮಿಕಂಡಕ್ಟರ್ಸ್. ನೇರವಾಗಿ ಸಬ್ಜೆಕ್ಟಿಗೆ ಹೋಗುವ ಮೊದಲು ನಾವು ಇವತ್ತು ಯಾವುದನ್ನೆಲ್ಲ ನೋಡ್ತೇವೆ ಅಂತ ಒಂದು ಸ್ವಲ್ಪ ನೋಡ್ಕೊಳ್ಳುವ. ಓಕೆ, ಪ್ರೆಸೆಂಟೇಷನ್. The content of this lecture will be history of semiconductors, semiconductor materials, direct and indirect gap semiconductors, intrinsic and extrinsic semiconductors, ಅದೇ ರೀತಿ formation of a p-n junction diode, then biasing of a p-n junction diode, then application of diode. ಈ ಇಷ್ಟು ವಿಚಾರದ ಮೇಲೆ ನಾವು ಸ್ವಲ್ಪ ಸ್ವಲ್ಪ ಮಾತಾಡಿ ನಿಮಗೆ ಅದರ ಒಂದು ಗ್ಲಿಮ್ಸ್ ಅನ್ನು ಕೊಡುವ ಪ್ರಯತ್ನ ಮಾಡ್ತೇನೆ. ಪ್ರಥಮವಾಗಿ ನಾವು ಸೆಮಿಕಂಡಕ್ಟರ್ ಹಿಸ್ಟ್ರಿ ನೋಡುವ. ಯಾಕೆಂದ್ರೆ ಯಾವುದೇ ಒಂದು ವಿಷಯದ ಇತಿಹಾಸವನ್ನು ನೋಡುವಾಗ ನಮಗೆ ಬಹಳಷ್ಟು ಅದರ ಮಹತ್ವ ಗೊತ್ತಾಗ್ತದೆ. ಈಗ 1782ರಲ್ಲಿ ಅಲೆನ್ಸಾಂಡ್ರೋ ವೋಲ್ಟಾ ಎಂಬುವರು ಫಸ್ಟ್ ಟೈಮ್ ಆಗಿ ಸೆಮಿಕಂಡಕ್ಟರ್ ಎಂಬ ಶಬ್ದವನ್ನು ಇಂಟ್ರೊಡ್ಯೂಸ್ ಮಾಡ್ತಾರೆ. ಆ ಶಬ್ದದ ಇಂಟ್ರೊಡಕ್ಷನ್ ಆದ ನಂತರ ಫೈಲ್ ವೋಲ್ಟಾ ಎಂಬುವರು ವೋಲ್ಟೈಕ್ ಫೈಲ್ ಎಂಬ ಒಂದು ಡಿವೈಸ್ ಅನ್ನು ಅನ್ವೇಷಣೆ ಮಾಡ್ತಾರೆ. ಅದೇ ರೀತಿ ಹಂಪಿ ಡೇವಿ ಎಂಬುವರು ಈ ವೋಲ್ಟಾ ಫೈಲ್ಸ್ ಅನ್ನು ಬಹಳ ದೊಡ್ಡ ಮಟ್ಟದಲ್ಲಿ ಅಭಿವೃದ್ಧಿಗೊಳಿಸಿ 100 ವೋಲ್ಟ್ ಅನ್ನು ಅಭಿವೃದ್ಧಿ ಮಾಡ್ತಾರೆ. ಈ ಕಾರಣದಿಂದಾಗಿ ಅವರಿಗೆ ಈ ಬೇರೆ ಬೇರೆ ವಸ್ತುಗಳ ಉಷ್ಣತೆಯ ಆಧಾರಿತ ಗುಣಧರ್ಮಗಳನ್ನು ಕಲಿಯುವಂಥ ಅವಕಾಶ ಒದಗ್ತದೆ. ಅವರು ಕಾಪರ್, ಸಿಲ್ವರ್, ಟಿನ್, ಲೆಡ್, ಐರನ್, ಪ್ಲಾಟಿನಂ ಇಂಥ ಬೇರೆ ಬೇರೆ ವಸ್ತುಗಳ ವಾಹಕತೆಯ ಬಗ್ಗೆ ಅಭ್ಯಾಸ ಮಾಡ್ತಾರೆ. ಆ್ಯಂಡ್ ಇದು ಸೆಮಿಕಂಡಕ್ಟರ್ ಸ್ಟಡಿಯ ಸ್ಟಾರ್ಟಿಂಗ್ ಡೇಸ್. ನಂತರ the famous Michael Faraday continued the work done by Davy. ಅವರು ಕೂಡ ಬೇರೆ ಬೇರೆ ಆಕ್ಸೈಡ್ಗಳು, ಸಲ್ಫೈಡ್ಗಳು, ಕಾರ್ಬೋನೇಟ್ಸ್ಗಳು, ಮರ್ಕ್ಯುರಿ ಅಯೋಡೈಡ್ಗಳು ಇಂಥ ಬೇರೆ ಬೇರೆ ವಸ್ತುಗಳ ಮೇಲೆ ಅಧ್ಯಯನ ಮಾಡಿ ಅವು ರೂಮ್ ಟೆಂಪರೇಚರಲ್ಲಿ ಅವುಗಳ ವಾಹಕತೆಗಳನ್ನು ಅರ್ಥ ಮಾಡಿಕೊಳ್ಳುವಂಥ ಪ್ರಯತ್ನ ಮಾಡ್ತಾರೆ. ಆಗ ಕೂಡ ಸೆಮಿಕಂಡಕ್ಟರ್ ಬಗ್ಗೆ ಸ್ಪಷ್ಟವಾದ ಮಾಹಿತಿ ಇರಲಿಲ್ಲ. ನಂತರ ದಿನಗಳಲ್ಲಿ ನಾವು ನೋಡಿದರೆ ಜಾನ್ ವಿಲಮ್ ಲಿಟಾಫ್ ಹೇಳುವರು ಬೇರೆ ಬೇರೆ ಎಲೆಕ್ಟ್ರೋಲೈಟ್ಸ್ಗಳನ್ನು ತಗೊಂಡು ಅದರ ವಾಹಕತೆಯನ್ನು ಸ್ಟಡಿ ಮಾಡ್ತಾರೆ. ಅವರು ಗ್ಯಾಸಸ್ ಆಲ್ಸೋ, ಈ ಸ್ಟಡೀಸ್ ಗ್ಯಾಸಸ್ ಆಲ್ಸೋ, he studies physics of cathode rays, so that lot of information about the conductivity of these materials are understood by these people. Later, the famous Edwin Herbert Hall, the one who invented the Hall effect, studied various materials and thereby he is able to differentiate the two types of charge carriers, that is positive charge carriers and negative charge carriers. Today you know that there are two types of positive charge carriers. Hall effect is the simplest experiment is to determine what is the type of charge carriers. Later, Carl Baedeker in the year 1907, he used thin films of metals. Remember, during those days he used the technique of sputtering. ಸ್ಪ್ರೇ ಮಾಡಿ ಥಿನ್ ಫಿಲ್ಮ್ಸ್ ಅನ್ನು ಡೆವಲಪ್ ಮಾಡುವಂಥ ಟೆಕ್ನಿಕ್ ಅನ್ನು ಅವರು ಮಾಡಿದ್ರು. ಅದರಿಂದ ಸಲ್ಫರ್, ಸೆಲೇನಿಯಂ, ಆರ್ಸನಿಕ್, ಅಯೋಡಿನ್ ಹೀಗೆ ಬೇರೆ ಬೇರೆ ವಸ್ತುಗಳ ಥಿನ್ ಫಿಲ್ಮ್ಗಳನ್ನು ಮಾಡಲಿಕ್ಕೆ ಪ್ರಯತ್ನ ಮಾಡಿದ್ರು. ಅವುಗಳ ಕಂಡಕ್ಟಿವಿಟಿಯನ್ನು ಅಧ್ಯಯನ ಮಾಡುವಾಗ ಅವರಿಗೆ ಬಹಳಷ್ಟು ಉತ್ತಮವಾದ ಮಾಹಿತಿಗಳು ಸಿಗ್ತವೆ. ನಂತರ 1910 ವೀಸ್ ಅವರು ಫಸ್ಟ್ ಟೈಮ್ ಸೆಮಿಕಂಡಕ್ಟರ್ ಎಂಬ ಪದವನ್ನು ಅವರ ಡಾಕ್ಟರಲ್ ಥೀಸಿಸ್ ಅಲ್ಲಿ ಉಪಯೋಗಿಸ್ತಾರೆ. ವೀಸ್ ಯೂಸ್ ದ ಟರ್ಮ್ ಸೆಮಿಕಂಡಕ್ಟರ್ ಇನ್ ಹಿಸ್ ಡಾಕ್ಟರಲ್ ಥೀಸಿಸ್ ಫಾರ್ ದ ಫಸ್ಟ್ ಟೈಮ್. ಅಂಡ್ ಲೇಟರ್ ಇನ್ ದ ಇಯರ್ 1930 a person by name Gooden, he studied the electric conductivity of various materials, particularly semiconductors, and he was with firm belief that pure materials cannot be semiconductors. If you want have a semiconductor, the pure metal has to be mixed with something else. That is the year of 1930. Later, in the year 1931, the famous R.H. Fowler is one of the very, very famous professor of Cambridge University, published a paper on semiconductors, and he classified between intrinsic and extrinsic type of semiconductors. And that is the beginning time of understanding the term semiconductor. And the entire evolution has taken place in the year 1948 when transistor was invented by three people, that is William Shockley, John Bardeen and Walter Brattain. You know, these are the three people who invented transistor in the 1947-48. Today, because of transistor, world is so beautiful. We make use of day-to-day life. Every aspect of our life is depending on this kind of invention, particularly transistor, because we know we are much dependent on the electronic gadgets. Most of them work based on these semiconductor materials, particularly transistor. Therefore, it was the year 1948 in the history of semiconductor revolutionized. Afterwards, lot of advances are done, taken place, as well as people worked in various fields so that semiconductor become an integral part of our life. ನಮಗೆ ಈಗ ಸೆಮಿಕಂಡಕ್ಟರ್ ಅನ್ನು ಬಿಟ್ಟು ಜೀವನ ಮಾಡುವ ಪರಿಸ್ಥಿತಿ ಇಲ್ಲ. ಅವು ನಮ್ಮ ಜೀವನದ ಅವಿಭಾಜ್ಯ ಅಂಗ ಅಂತ ಆಗಿದೆ. ಅದ ಕಾರಣ ಸೆಮಿಕಂಡಕ್ಟರ್ಸ್ ಬಗ್ಗೆ ತಿಳ್ಕೊಳ್ಳುವುದು ನಮ್ಮ ಧರ್ಮ ಅಂತ ನಾನು ಭಾವಿಸ್ತೇನೆ. ಈಗ ಸೆಮಿಕಂಡಕ್ಟರ್ಸ್ಗೆ ಕನ್ನಡ ಪದ ಅಂದ್ರೆ ಅರೆವಾಹಕಗಳು. ವಾಹಕಗಳು ಅಂದ್ರೆ ಎಲ್ಲ ಮೆಟಲ್ಗಳು, ಲೋಹಗಳೆಲ್ಲ ವಾಹಕಗಳು. ಅಲ್ಯೂಮಿನಿಯಂ, ಕಾಪರ್ ಇವೆಲ್ಲ ವಾಹಕಗಳು. ಸೆಮಿಕಂಡಕ್ಟರ್ಸ್ ಅರೆವಾಹಕಗಳು. ಅದೇ ರೀತಿ ವಾಹಕತೆ ಇಲ್ಲದವುಗಳು, ಮರ ಫಾರ್ ಎಕ್ಸಾಂಪಲ್, they are all insulators. They do not conduct electricity. Therefore, we'll try to understand the basic physics behind the semiconductor materials. So when somebody asks you, what is a semiconductor? Now, what is your answer? Normal student will answer like this. Group of materials having electrical conductivities intermediate between metals and insulators. ಅವುಗಳ ವಾಹಕತೆಯು ಮೆಟಲ್ ಮತ್ತೆ ನಾನ್ ಮೆಟಲ್ಸ್ ಮಿಡ್ಲಲ್ಲಿದೆ. ಇದೊಂದು ಸಾಮಾನ್ಯವಾಗಿ ತುಂಬಾ ತಿಳಿಯದ ವಿದ್ಯಾರ್ಥಿಗಳು ಅಥವಾ ಸಾಮಾನ್ಯರು ಕೊಡುವಂತ ಉತ್ತರ. ಇದು ತಪ್ಪಲ್ಲ, ಇದು ಸರಿ. ಆದರೆ ವಿಜ್ಞಾನದ ವಿದ್ಯಾರ್ಥಿಗಳಾಗಿ ನಾವು ಈ ರೀತಿ ನೆನಪಿಟ್ಕೊಳ್ಬೇಕು. ಕಂಡಕ್ಟಿವಿಟಿ, ವಾಹಕತೆಯನ್ನು ನಾನು ಮೆಜರ್ ಮಾಡಿದರೆ ಸಿಮೆನ್ಸ್ ಪರ್ ಮೀಟರ್ ಅಲ್ಲಿ ಮೆಟಲ್ಸ್ ಅಲ್ಲಿ 10⁻² to 10⁸ 10⁻²ರಿಂದ 10⁸8 ಇದು ಮೆಟಲ್ಸ್ ಕಂಡಕ್ಟಿವಿಟಿ. ಸೆಮಿಕಂಡಕ್ಟರ್ಸ್ ಅಲ್ಲಿ 10⁵ರಿಂದ 10⁻⁻6 10⁻⁵ to 10⁻⁻6. ಇನ್ಸುಲೇಟರ್ಸ್ ನೋಡಿದ್ರೆ 10⁻⁻6 to 10⁻⁻11. This is conductivity. I am talking about conductivity. ವಾಹಕತೆ. ರೆಸಿಸ್ಟಿವಿಟಿ ಅಂತ ಹೇಳಿದ್ರೆ ಇದನ್ನು ನೀವು ಡಿನಾಮಿನೇಟರ್ ಅಲ್ಲಿ ಬರೆದು ನ್ಯೂಮರೇಟರ್ ಅಲ್ಲಿ 1 ಅಂತ ಬರೆದ್ರೆ ಅದು ನಿಮಗೆ ರೆಸಿಸ್ಟಿವಿಟಿ ಕೊಡ್ತದೆ. ಅಥವಾ ಇನ್ ಎ ಬೆಟರ್ ಲ್ಯಾಂಗ್ವೇಜ್, ಈ 10⁻² ಅನ್ನು 10⁻⁻2 10⁻8 and 10⁻⁻8 ಅಂತ ಬರೆದ್ರೆ ಅದು ರೆಸಿಸ್ಟಿವಿಟಿ ಆಗ್ತದೆ. ಅದ ಕಾರಣ as a student better to remember this idea. Semiconductors particularly, the conductivity is in the range of 10⁵ to 10⁻⁻6 Siemens per meter. Now, what is very important is this is a general idea of definition of semiconductor, but this conductivity of these materials can be varied very much by changing the temperature, optical excitation or impurity of the content. What you add as impurity or mix this original semiconductor materials, depending on that, the conductivity can be increased or decreased. Similarly, temperature dependence is also a very important aspect. optical excitation can be done. Therefore, you can see that some amount of light falls on these materials, the conductivity can be increased. Such materials are also found. Therefore, this is the general definition of a semiconductor material. Always we have to look at this table. You look at this table, this is a part of the periodic table. I am talking about the group 2 elements, group 3 elements, group 4, group 5 and group 6, the first table you can see. Just to concentrate on the group 4. In the periodic table, group 4, you find that carbon, silicon, germanium. What is the specialty of group 4 elements? Group 4 elements always have the outermost electron in the valence shell is equal to 4. Therefore, the 4 represents that. That represents the outermost electrons available in the atomic structure. Carbon, silicon, germanium. Therefore, these are the materials. As such, they behave like semiconductors. Therefore, they are called elemental semiconductors. You see the list in the next table. I have made a list. Silicon and germanium are called elemental. Andre adu param elemental state alli semiconducting materials. Now they are very few in numbers, but what people can do, they can combine two elements. For example, silicon and carbon can be combined. Silicon and germanium also can be combined. If you combine these two materials, compound, now it becomes a compound material. This also acts like a semiconductor. Just you are combining two elements of the same group, like silicon and carbon. Next, you can have two different compounds. That is called binary compounds. Binary compound means one element from the group 3, another element from group 4, sorry, group 5 are combined. See, in the group 3, for example, you see aluminum and phosphate, ALP. Aluminum, outermost electrons 3 in numbers. Therefore, valence of the aluminum is 3. Similarly, phosphorus, if you look at it, it is a pentavalent. Pentavalent means outermost electrons are 5. This aluminum and phosphorus, two atoms are combined. As a result, two atoms have 3 plus 5, that is 8 valence electrons in the outermost shell. When they come to see that 4 electrons each available in either of the atoms. Therefore, again, they can behave like semiconductor. The primary requirement for semiconducting, general semiconductor, is there should be 4 valence electrons per atom. Here we have 2 atoms, 8 electrons shared between the 2 atoms. Therefore, 4 each again. This way, you can prepare a binary compound of semiconductor. Therefore, there is aluminum phosphate, aluminum arsenate, aluminum, what is that, SB, gallium nitrate, gallium phosphate, gallium arsenate, like that. Element goes on that. Okay. They also act like binary compound semiconductors. Next, see the next column here. I am talking about this column here. This column where you find that you have element from the group 2 and element from group 6 are combined. Again, zinc and sulfide. Zinc is available at group 2, sulfur is available in group 6. Zinc has 2 valence electrons, sulfur has 4 valence electrons. As a result, if you combine them, again 6 plus 2, 8 electrons shared between the 2 atoms, you find that 4 electrons each in combination. Again, it becomes a semiconductor. You see that zinc sulfide, zinc selenium, zinc telluride, cadmium sulfate, cadmium telluride, cadmium telluride. So these are the different combinations of compounds. They are called binary compound, binary 3,5, binary 2,6 compounds. Next, along with that, we can have some other materials. Recently, that is the last 40 years, people have identified various new types of materials, particularly the organic materials. See, anthracene is an organic compound. Similarly, phthalocyanine is an organic compound. If you dope phthalocyanine with some dopants, or anthracene as such behaves like a semiconductor. Their conductivity lies in that range of conductivity. That is important. Nowadays they are very useful materials. That particularly organic semiconductors are useful in organic LEDs, that is organic light emitting diodes, and they are much useful in the light related applications. Similarly, organic polymers. You see that polymer is a long chain of monomers, you know that. Polypyrrole, polyaniline, polythiophene, these are the materials which are polymer materials. They also show this semiconducting property. Because of that, the semiconductor field is available even in the polymer area, even in the uh, light related applications, everywhere. These are the three new kind of materials which is very useful nowadays. Okay. Yeah. Now let us have look at the structure of this type of materials. Say most of the semiconductor materials have this kind of structure. This is called diamond kind of structure, diamond structure. Similarly, zinc blende structure, there are some of the materials which show zinc blende type of structure. What is the specialty of this structure? So most of them are in FCC, that is a face centered cubic structure. That means all the corners there is one atom, and every face of the crystal structure, the 6 faces, there is an atom. Not only that, there are diamond kind of structure. Why the diamond kind of structure is, if you look at every element, you look at every atom here. Look, for example, this atom. If you look at this atom, see, you can see that there are 4 bonding sites. Look at this atom. Okay. For example, here, look at this. Okay, there are 4 nearest neighbors. See, look at here, 4 nearest neighbors. There is 1, 2, 3, 4. This kind of structure is normally referred as diamond kind of structure. And they show unique properties of behaving like covalent materials. They are bonded by the covalent bond. Probably you have heard the covalent bonds. What do you mean by covalent bond? That is, bonding takes place between 2 atoms by sharing of electrons. Therefore, electron sharing plays an important role here. Okay. Similarly, if you combine the that third and fifth group elements, then their structure will be sorry their structure will be uh, group, write it here, say third and fifth group elements, then zinc sulfide, for example, that shows a kind of structure which is called zinc blende structure. Therefore, most of the semiconductors show this kind of diamond structure. Example, silicon, germanium, and even carbon shows this kind of structure. Therefore, that is the very uniqueness of this material. That is, every atom has 4 nearest neighbors. Bonding takes place between 4 nearest neighbors through sharing of electrons. Again, I was talking about the covalent bond. Covalent bond is, I told you, it is the sharing of electrons. Sharing of electrons. and it is one of the very strongest bonds. Now, if you look at the electron configuration of this silicon, you know that atomic number is 14 for silicon. Therefore, there are 14 atoms, 14 electrons. To see that first shell is complete by 1s2, second shell is complete by 1s2 and 2p6, because you know that first shell can occupy 2 electrons, second shell can occupy 8 electrons according to the electron distribution in the shells, and outermost shell has 3s2 as well as 3p2 electrons. Since the 10 electrons, that is two shells are complete, we go for the neon representation. That is, the neon is atomic number 10, where you can go for the neon followed by 3s2 and 3p2 configurations. Therefore, you see that there are two s electrons and two p electrons in the outermost shell. So that is the beauty of this type of materials. Now, if I look at it, these 4 electrons in the outermost shell, which are partially filled, you know that, and you look at just if you go back and concentrate at this, what will happen? There will be bonding takes place. Bonding. Now, when I say bonding, what type of bonding? Say this s orbitals always go for spherical kind of bonding. Spherical kind of bonding. Spherical bonding. Okay. So this is a, if I write it x, y, z, then spherical kind of bonding takes place in the case of s orbitals. And when I say p orbitals, it is always, you find that they're in a double dumbbell. Okay, dumbbell shaped orbitals. Probably you studied this in chemistry. You find that orbitals are like this. Okay, for various x, y, z, if you take px and py orbitals, similarly pz orbitals. Here, the electrons will interact between s and p orbitals, which will lead to hybridization. Probably you heard this term hybridization. That is called sp3 hybridization. sp3 hybridization is a kind of hybridization takes place between the sharing of electrons. Again, you probably you studied it chemistry, of course. I hope you are able to get this point, what I am trying to say. Now, if you visualize the crystal structure in 3 dimension is fine, but it is much easier to visualize the structure if you go for a 2-dimensional view. Now, this is the picture of silicon crystal view in a particular plane. For example, in 11100 direction, if you view the crystal structure of silicon, you find structure like this. You see, as I told you, each one is a silicon atom. See, there are two lines. Two lines means bonding takes place between one electron shared from this, one electron shared from here. Therefore, each line corresponding to one electron. Therefore, always double bond. Everywhere you see that 2 electrons per bond is spent. That is, for example, if you take this silicon atom, it has got 4 nearest atoms of silicon. Each one will contribute 1 each, and it has got 4 electrons. Therefore, these 8 electrons contribute 4 double bonds of covalent bond. Okay, that is the share. Therefore, it is said here the forces binding covalent bond, that is, the bonding forces arise from the quantum mechanical interaction between the shared electrons. This is known as covalent bonding. Each electron pair constitute a covalent bond. It's a very strong kind of bonding. How the bands are formed? Bonding is fine. Now, to understand the behavior of the material, you should know what is a bond. For example, if you take a crystal of silicon with n atoms, then there are 4 n electrons and 8 n discrete levels. I hope you are able to get it. Because each atom contributes 4 electrons in the outermost shell, and you know that in each shell there are possibility that you can occupy 2 electrons. Therefore, these 2 electrons may go for 2 different states. As a result, you have double number of discrete states. That is 8 n discrete levels. Therefore, once I say there are 8 n discrete levels for the energy, that is electron to occupy. Now, how close they are? Probably you studied the hydrogen atom and its energy levels. You know that hydrogen, there is one electron which is available in the hydrogen atom. When you find a group of electrons together, because a group of atoms together, the electrons with similar energy or almost same energy, they come together, they form a group and they occupy at certain levels. These levels are referred as the bands. Here also, the energy levels of these electrons are so close that you cannot differentiate between the levels. Therefore, I can express this as say very, very close by levels. These are very, very close levels. Okay. Different electrons, their energy is almost close, almost close. Therefore, this kind of arrangement is referred as bands. And for us, it looks like a continuous band, continuous bands. Therefore, there are few electrons with this kind of energy, and there may be some more electrons at a different level. I'll show here different lines. They may form another band. Okay. Therefore, we can visualize that there are different levels of bands when atoms come closer in a crystal. Therefore, you remember, if I talk about any crystal, there will be huge number of atoms, like 10 to the power of 22 atoms per meter cube. If you think of 1 meter cube of a crystal, then there are 10 to the power of 22 atoms. Therefore, I hope you are able to visualize this number. It's a very large number. 10 to the power 22 is a very large number. Therefore, all those electrons have similar energy. They come together. They form a band. Okay. Therefore, idea of band arises because of this. Say, I told you already. Now, as I told you here, if they form bands at 2 different levels, there is some gap in between, right? Between these 2 bands. That is referred as energy gap. Okay? That is referred as an energy gap. So always remember, at electrons occupy a certain levels, it's separated by a certain gap. This is referred as energy gap. And many of the cases in metals as well as semiconductors, you see that lower band is completely occupied by 4n valence electrons at absolute zero temperature. At 0 Kelvin, all those electrons occupied at the lowest level is referred as valence band. And if you go to another band, that is higher level, the higher level band is referred as a conduction band. At 0 Kelvin, all these bands are empty. Therefore, you remember, at 0 Kelvin, all the electrons are occupied at lowest energy level, that is called the valence band level. And conduction band, higher energy level, no electrons are present. Conduction band is completely empty at 0 Kelvin. Again, I'm specifically saying 0 Kelvin is absolute zero. Absolute zero, any material will behave like a bad conductor because conductors conductivity is due to the movement of electrons. At 0 Kelvin, there are almost no electrons at the conducting level. They're all like slipping. They do not contribute for the conduction. This is very important point to remember. Now, as I told you that time, orbitals, formation of bands, how the orbits form, just I explained with the help of the diagrams. Say, the silicon atom, I have told you, you have a spherically symmetric s orbitals. Now, this understood with the help of a term called wave function quantum mechanically. Similarly, if you think of the p orbitals, you have px, py, and pz orbitals. They are all dumbbell shaped, and you see that if they are having the equal probability of occupation, then they look like double dumbbell. You see in one of the case here, you see that is only py orbital, equal spacing between the positive and negative charges are found. When this s and py orbital combines, you see that hybridized orbital looks like the third diagram. Okay, third diagram, where one is expanded further, other one is reduced in the size. That is how sp3 hybridization is imagined with the help of wave function. Okay. Similarly, very interestingly, the behavior of these materials or these electrons is studied with the help of a term called wave function. Wave function is always talks about the probability of finding the electron. How they are probable? See, if you look at it, atomic orbital, there are two functions, psi1 and psi2. Psi1 and psi2. Their probability is maximum at the around the middle point. Okay, and how they combine important. If they combine like if they combine like say this kind of diagram, that is positive and negative go to different levels, then that is called anti-bonding orbital. Here, if they're of same type, then they're called bonding orbitals. Therefore, remember a very important thing is this linear combination of the wave functions takes place. Linear combination. Mathematically, we call it as a linear combination of atomic orbitals leading to bonding orbital and anti-bonding orbitals. That is odd wave functions. Look at it. Say these are the odd wave functions. Okay, that is one is in the top probability, other one is in negative side. Therefore, these odd wave functions always lead to anti-bonding. This is odd wave function. Okay, odd wave functions. Similarly, even wave functions, then that will lead to bonding orbitals. Always remember that is symmetric. Wave functions even or we call symmetric wave function. This is anti-symmetric wave function. Symmetric wave functions lead to bonding orbital and anti-bonding orbital is due to the non-symmetric wave functions. Okay, always remember bonding energy level is always at a lower level and anti-bonding energy is always at a higher level because bonding will lead to constructive activity here you see, whereas anti-bonding will lead to the not constructive, we say the destructive kind of arrangement. And this is a very popular diagram you see in all the books. So you see insulator, we say filled band at the lower level, and at the higher level you have vacant band. The energy gap is of the order of or greater than 5 electron volts. Then we call it as an insulator. So here, filled band, empty conduction band, filled vacancy band. So this is our valence band. This is valence band. This is valence band and this is the conduction band. Here you see the energy gap is of the order of 1 to 2 electron volt. 1 to 2 electron volt. Okay. In the case of metals, you find that partially filled valence band and overlapping conduction band. Both here already electrons available. Therefore, they conduct at 0 Kelvin also. You can think that they have conductivity, but of course, it is negligibly small. Typical structure at 0 Kelvin. Physically, I am talking about 0 Kelvin. Now, one other important term I want to tell you about the direct and indirect band semiconductor, which you normally don't study at your school level. See, bands are represented with the help of this hyperbolic type of structure. One is you find that this kind of structure, other one is the opposite to that. See, that energy versus K. K is the wave vector, we call wave vector. K is the wave vector. And you see that lowermost point of the conduction band and the topmost level of the valence band, they have same K value. Remember, same K value because vertically they are in the same point. Such semiconductors are called direct energy band gap semiconductors. Direct band gap semiconductors. In the second diagram, you see that the conduction band lowermost point is somewhere here, valence band is somewhere here. Therefore, to take an electron from valence band to conduction band, not only energy is sufficient, you require some K also, that is the momentum also is to be supplied. Therefore, they are referred as indirect band semiconductors, indirect band semiconductors. Therefore, try to understand this valence band, conduction band not at the same K value. Additional K, that is K refers to momentum, is required for the conductivity. Hence, they are called indirect band gap semiconductors. These are all, I am talking about the basic aspects of semiconductors in their structure, bonding formation, as well as how they behave when the energy vector, energy versus K vector varies. Next, we'll go for very important aspect semiconductor. The perfect semiconductor crystal with no impurity or lattice defect is called intrinsic semiconductor. There should not be any impurity. There should not be any defects in the material. Such materials are referred as intrinsic semiconductor. Even at 0 Kelvin, they do not conduct. Remember, they do not conduct at 0 Kelvin also because valence band is completely filled and conduction band is completely empty. That is the specialty of intrinsic semiconductors. You just look at here. In the case of intrinsic semiconductor, there will be equal number of electrons and holes. You look at this is silicon crystal again. I am showing you. Suppose one bond is broken by thermal excitation or by some means. If you are able to break one bond, then one electron is liberated. At the same time, one absence of electron, which is called the hole, is also liberated. Therefore, remember, in intrinsic semiconductor, the number of positive charges, number of negative charges, that is the charge carriers, number of positive charges or number of negative charges remains the same. Therefore, at intrinsic symmetry, we say electrons is equal to holes, number of electrons is equal to number of holes. That we refer as Ni, intrinsic charge carrier. Number of intrinsic charge carriers, that is the electrons or hole, whatever you take. They have equal number of N and P, electron or hole. Now, what is extrinsic semiconductor? As I told you, semiconductors at intrinsic nature is of no use because they do not contribute much for the conductivity. Now look at, it is possible to create some usefulness from the semiconductors by mixing something. How to mix is very important. We have to mix it with a purpose. purposefully you are mixing it. How much you are mixing it? Very much less. That is what is we call it as ppm. That is parts per million. Means one atom of impurity to about 10 to the power of 6 atoms of silicon. One atom impurity is sufficient to create a extrinsic semiconductor for 1 million atoms of silicon. Therefore, this type of mixing of impurities is referred as doping. Okay, I hope it's clear to you. Purposefully and known amount of impurities you are adding. Now, how much doping you have to do? As I told you, 1 into 1 is to 10 to the power 6. In language of science, we call traces. We are adding traces, very small quantities of this type of material. Traces you are adding. Okay. Therefore, two types of dopants you can think of. You can add the materials which can donate the electrons, which are donors, or you can add materials which can accept the electrons. Depending on that, you have N-type semiconductors and P-type semiconductors. When I say N-type, it has excess of electrons. When you say P-type, it has excess of holes in that. Therefore, when a crystal is doped such that at equilibrium, carrier concentrations are different from intrinsic carrier concentration. That means you are imbalancing the equilibrium of concentration by adding excess of electrons or excess of holes. This process is referred as doping. Now, you look at it, say I am adding one arsenic atom. Okay, here I'm adding one arsenic atom. Arsenic. You know that arsenic is pentavalent. Therefore, it will contribute to 5 electrons from the outermost shell. As a result, you see that these 4 electrons are shared by this 4 nearest neighbor and additional electrons are available. If you add arsenic, then it becomes N-type semiconductor because it will create additional electrons. Similarly, here we are showing boron. Suppose you add a boron atom in the place of a silicon, then 3 outermost electrons of the boron are shared by 3 neighbors. For the one electron of the neighboring silicon, there is no pair given by the boron. As a result, you see that one vacancy is created that is called a hole, and the material becomes p-type material. Therefore, adding a pentavalent material will give you a n-type material. Adding a trivalent, three valence atom to silicon will give you a p-type material. This is what is the entire process of making n-type or p-type materials. That's what I told you. I already explained you the elements 3 and 5. Next, now as such, these element materials may not be much use for us. Therefore, we have to have some devices on that. The simplest device is called PN junction diode. That is called diode. Okay, PN junction diode. The symbolically we write like this: a diode. P side and this is N side. P side and N side. Semiconductor diode. Okay, a semiconductor diode. Now, you cannot simply combine two junctions, P or N type. It is not possible. Mechanically, if you bring them together, it is not possible. There are various methods. What they do is normally in one end N type metal is added, other end P type metal is added. They are creating a P N junction as such. Now, what will happen if you look at it? In the P type side, you have more holes, whereas in N side, you have more electrons. When you bring them together, there is a imbalance here. Okay, that is called the. As a result, you find the process called diffusion. Diffusion. because there's a gradient created, gradient in terms of number. Here you have excess of holes, you have excess of holes, electrons, positive charges here. When you bring them together, there will be gradient, okay? That gradient refers to imbalance of charge carriers. Imbalance. As a result, when suppose one electron goes from this side to from the right side to the left side in your screen, then it will leave a positive ion either the neighboring place. Similarly, if a hole comes from the left side to right side, then it will leave an negative ion in that nearby. As a result, if you look at the middle region, you see that there will be negative charge carriers in the p side, positive charge carriers in the n side. That means there will be ions. The atoms are depleted and you are creating some ions. This region is referred as the depletion region. Therefore, electrons and holes diffuse in the opposite direction, creating a region where only ions present, positive and negative ions. That region is referred as the depletion region. You see that once they diffuse each other, further diffusion of electrons or holes from either side is prevented because it itself will act like a barrier. Okay, this barrier is referred as the potential difference, okay, which will prevent the electrons or holes diffusing from either side. Okay, this is the barrier potential, we know. Therefore, once the junction is formed, because of the creation of this barrier potential, further diffusion of electrons or holes are stopped and a PN junction is formed. Very important one. A PN junction is formed. That means one side you have electrons, excess, on the other side, holes excess, but in between certain region, only ions are present. Okay, this is the formation of a PN junction. Again, once you have a PN junction, what is the use of it? It may not be useful. Therefore, what we do, we try to make use of the device as I told you for the bias application. What we do is, we will bias the PN junction. What do you mean by biasing? Applying external voltage from a battery. Suppose you connect the P side as I shown in the diagram, P side to a positive of the battery and N side to the negative of the battery, then from the battery, from the N side, here you see here, the negative side, the positive side, excess of electrons will be getting here, excess of electrons will come here, similarly excess of positive charges will come here. As a result, what will happen? The region between the junction, that is the depletion region, it will reduce in the size, right? Reduce in size. Therefore, what will happen when the depletion region reduces? It allows electrons or holes to go through from one side to other side. As a result, we find that more number of electrons are flowing like this, or otherwise to say more positive charges will flow like this. Flowing of this electron from N side to P side, or flowing of holes from positive side to N side, will give rise to a current. This is the direction of the current from P side to N side. As a result, we say diode is forward bias. Okay, forward bias. Diode is forward bias. In the process of forward biasing, depletion region reduces, the resistance there reduces, and current flows from P side to N side, or in other words, electrons flow from N side to P side. That is the meaning of forward biasing of a PN junction. Similarly, now what will happen if you excess of voltage if you use it? This is the voltage which I told you, the biasing voltage. Okay, biasing voltage. If you increase the biasing voltage and barrier potential goes on decreases. You see that barrier potential without battery is number one, is without battery. If you apply battery, then barrier potential decreases. Further, if you apply higher voltage, barrier potential decreases. Say for the maximum here, when I use this voltage is much less than this because you are given the amount of voltage that is called the barrier potential here, you apply external voltage, you apply. External voltage will reduce the barrier potential so that current flows from P side to N side. That is forward biasing of the diode. Then reverse biasing. What do you mean reverse biasing? You see that negative side is connected to P end, positive of the battery is connected to N end. As I told you, here electrons will be injected here, positive charges will be injected here. More electrons are injected here. Already in the depletion region, there are electrons. Their number increases further. Here, from positive charges, the depletion region, their number increases further. As a result, the width of the depletion region increases, W increases compared to the original condition, it increases. When that width increases, what will happen is, it will give more resistance for the flow of electrons from either side. As a result, higher resistance will be there at the junction, and still there may be little current in the reverse bias junction also because of the minority carrier. Some of the electrons are able to cross the junction, although width of the depletion region is more, they are successful in crossing the other side, giving rise to little current. That is called reverse bias current. Reverse bias current. You see here, this is the original barrier potential, V0. If I apply barrier potential, for one, it is so much. For higher value, it further increases. Therefore, very interestingly, if you increase the biasing voltage, the barrier potential will increase. There will be little current, of course, as I told you, that is due to the minority carriers. This is the diagram which I am trying to explain you with the help of these three diagrams. To see that first case, depletion region, the first diagram here, when the junction is formed, when forward bias, this will happen, depletion region decreased in the middle. Here you see depletion region increased. Here also, with the help of the band diagrams, I can show you. V0 is the barrier potential. Okay, barrier potential you see here, because of applied forward voltage, barrier potential decreased. Compared to the first one, you see, compare the first one and second one, barrier potential decrease. When you reverse bias it, first one and the last one, barrier potential increase. Because here barrier potential is subtracted because of the positive side connected to P side. Here barrier potential is added to this so that barrier potential increases. This also can be explained in terms of band diagram, which is not much useful for you at this juncture. So this is how we understand the characteristics of a PN junction diode. What we do, we measure the, suppose you have a diode like this, okay, you connect a power supply here, a battery, you connect a battery, and you current meter here, millimeter or micrometer, and this is a simple circuit of a PN junction diode for the characteristics. And I connect a voltmeter across this diode. The voltmeter is connected here, and I have this experimental setup. This is the forward bias. P side is connected to a positive battery, N side is connected to this. I have a battery here, a millimeter here. I vary the voltage here and measure the voltage and current. I vary the voltage at the battery, measure the voltage and current. The forward bias, you get the current in the range of milliammeters. y-axis here, positive y-axis is millimeter, and here is the volt. And you see this is the junction potential you can measure, 0.6 in the case of silicon. Suppose you do the reverse bias, that is exchange the polarity of the battery, then you see that current is in microampere because it is due to the minority carrier. Negative y-axis you see is the microampere, and voltage you require higher voltage to get the current like this. Here voltage is in given in 100 and like 20, 40 like that, very large voltage compared to this. This is the characteristics of a PN junction diode. Now, one more important application of this diode is used as a rectifier. What is rectification? Rectification is converting two-dimensional current into a one-dimensional current. Where we find that we get AC from the dynamo, which is in the two-dimensional format. That is AC current or voltage is in two dimensions. Whereas that has to be converted into one direction, two direction current, one direction current. You see here, therefore we need a device called a rectifier. This diagram, we talk about a rectification, but in the first part we show a transformer. It's not a rectification part, but still we can show primary higher voltage is there. We convert it into a lower voltage by using a secondary here with a less number of turns. Probably study the transformer principle. Large number of turns in the primary, less number of turns in the secondary will lead to step down voltage process. Suppose you have step down voltage, some AC of some 10 volt, 6 volt, then one diode is connected here in this form with the help of a resistance here. And whenever current flows in the direction in the upper part here, that is P side and N side, look at it. P side is a higher voltage compared to N side, then diode will conduct as forward bias. As a result, you get some voltage here. Okay. But for the negative off cycle, the current will not flow there. Therefore, you don't find any voltage. For the second cycle, for the positive cycle, you get the voltage. Therefore, you are able to successfully convert all the positive sides of this AC to single side. That's what is called half-wave rectification. Half-wave rectification. You require one diode for this half-wave rectifier application. Of course, there is a filter and you can make it more linear form, but the principle is this. For the positive off cycle of the AC input, diode conducts. Correspondingly, you get the unidirectional current for the positive off only. For the negative off cycle, they do not conduct, hence you don't get any current or any voltage across this load. Therefore, after rectification input signal, output signals are shown like this. Now you think of a full wave rectifier. That is, I want to make use of both cycles, both positive and negative half of the input waveform. Then you use two diodes here, two diodes. But the important requirement is you have to have a center type transformer where it's connected like this. Center type is connected to this end of the load, and two diodes are connected like this. For the positive off cycle, you see that diode D1 will conduct and current flows in this manner. Current flows in this manner. Okay, you see that positive off cycle you get this way. For the negative off cycle, D2 will conduct, current will flow here again. Remember, current will flow again like this. Because diode is connected like this to this common point, it will flow. Therefore, across the load resistor, you see that current flows in the same direction for both off cycles. Therefore, we are able to successfully convert both off cycles of the AC input to unidirectional current. That is referred as the full wave rectifier, full wave rectification. Therefore, this is the basic circuit required to convert AC to DC. We call alternate current to direct current. Half wave rectifier as well as full wave rectifier. Okay. Then some other important applications I will mention here. One is Zener diode, where you have a PN junction diode with heavily doped regions. Heavily doped regions. This Zener diode is useful for voltage regulation applications. Voltage regulation. Okay. Voltage regulation applications, you can make use of Zener diode. Symbol of Zener diode will be like this. We write Z here. Okay. Instead of straight line, we write a Z like such. This is P side and N side. It is useful for voltage regulation. Therefore, whenever we want to use some any device, voltage input should be very constant. Therefore, the simplest application is the Zener diode, where you can control voltage and regulate the voltage. Say 5 volts, 1.5 volts, 10 volts, 12 volts, whatever you want, you can do by making such a Zener diode. There is an important application in semiconductor diode with the heavily doped region of Zener. Okay. Next one, photodiode. You know, from the name you can make out. Photodiode. When light falls, photo means light. When light falls on the junction of the diode, it will conduct. Photodiode applications, you find a lot of applications. These photodiodes are useful in our TV remote sensors, where photons of all wavelengths can be detected nowadays. You can detect IR, infrared, you can detect visible light, everything. It will be useful for sensor applications. Then light emitting light, popularly known as LEDs, we call it as LEDs. Okay, and they are very useful for lighting. Nowadays, you have lighting applications, and this LED materials very very attractive nowadays. But one important point to remember is Zener diode can be made from a silicon or germanium, whereas photodiode, light emitting diode, or solar cells cannot be made from germanium or silicon. You should have the combination like this, the gallium arsenide, gallium nitrate. This kind of materials you require. Okay, gallium phosphate. This is the combination or compound semiconductors are required for this kind of material, because silicon is a direct band gap, sorry, indirect band gap material, whereas gallium arsenide, gallium nitride, gallium phosphate, all direct band gap materials. They are useful for light application. Therefore, remember, for light related applications, you require direct band gap materials. And solar cell, again, you know that sun's energy can be tapped with the help of solar cells. Of course, solar cells now lot of methods have come, including the silicon materials also useful here because they are cheap. You can make use of that silicon material. Efficiency is less, but still you can make use of them. And all this, what I am trying to say is, all are the applications of various semiconductors, whether it is photodiode, whether it is light emitting diode, or solar cell. Probably you know light emitting diode, the gallium nitride, the invention of gallium nitride by Suji Nakamura, which gave him the Nobel Prize, where he designed gallium nitride material composition in such a manner that it will emit the blue light, blue LEDs, or we say nowadays white LEDs, because blue LEDs, which is the higher energy side, using blue LEDs, we can store a lot of information in DVDs and storage devices. Even for reading applications, these blue LEDs are very useful. Therefore, information technology is revolutionized by the invention of gallium nitride LEDs. As a result, the invention got the Nobel Prize. Therefore, friends, I think I've taken a lot of time, and if you have a few important questions which you plan to ask, please ask. So these are the references. People can read these references. One very important book is there called Benji Streetman and Sanjay Kumar Banerjee. Very useful material for PU students as well as engineering students in the future. Similarly, you have your NCERT textbooks, which you can always refer. One more article I referred is George Bush, European Journal of Physics, just published in the 1989. Thank you.
Thank you, sir.
Yes.
Thank you, sir. Thank you so much, sir. ಸೊ ತಾವು ಕೊಟ್ಟಂತ ಈ ಒಂದು ಉಪನ್ಯಾಸ ಕಾರ್ಯಕ್ರಮವು ವಿದ್ಯಾರ್ಥಿಗಳಿಗೆ ಭಾರಿ ಸರಳವಾಗಿ ಕನ್ನಡ ಮತ್ತು ಇಂಗ್ಲಿಷ್ ಎರಡರಲ್ಲೂ ಕೂಡ ಸೆಮಿಕಂಡಕ್ಟರ್ಸ್ ಎಂದರೇನು, ಸೆಮಿಕಂಡಕ್ಟರ್ಸ್ ನ ವಿಧಗಳು ಹಾಗೂ ಪಿ ಎನ್ ಜಂಕ್ಷನ್ ಯಾವ ರೀತಿ ಫಾರ್ಮೇಶನ್ ಆಗುತ್ತೆ ಅನ್ನೋದ್ರ ಬಗ್ಗೆ ದೀರ್ಘವಾಗಿ ಮಕ್ಕಳಿಗೆ ಭಾರಿ ಅರ್ಥ ರೂಪದಲ್ಲಿ ತಿಳಿಸಿಕೊಟ್ಟಿರೋದಕ್ಕೆ ನಮ್ಮ ವಿಜ್ಞಾನ ಮತ್ತು ತಂತ್ರಜ್ಞಾನ ಇಲಾಖೆ ಅಕಾಡೆಮಿ ವತಿಯಿಂದ ಹಾಗೂ ನನ್ನ ವೈಯಕ್ತಿಕವಾಗಿ ಧನ್ಯವಾದಗಳು ಸರ್. ಅದೇ ರೀತಿ ಈ ಒಂದು ಕಾರ್ಯಕ್ರಮಕ್ಕೆ ಹಗಲಿರುಳು ಶ್ರಮಿಸುತ್ತಿರುವ ನಮ್ಮ ಮುಖ್ಯ ಕಾರ್ಯನಿರ್ವಹಣಾಧಿಕಾರಿಗಳಾದಂತಹ ಡಾಕ್ಟರ್ ಎಂ ರಮೇಶ್ ಸರ್ ಕೂಡ ನಮ್ಮ ಧನ್ಯವಾದಗಳು ಸರ್. ಅದೇ ರೀತಿ ನಮ್ಮ ಅಕಾಡೆಮಿ ಅಧ್ಯಕ್ಷರಾದಂತಹ ಐರ್ಫಾನ್ ಸರ್ಗೂ ಕೂಡ ಧನ್ಯವಾದಗಳು ತಿಳಿಸುತ್ತಾ ಈ ಒಂದು ಕಾರ್ಯಕ್ರಮಕ್ಕೆ ಅವರು ಹಾಜರಾಗಲಿಲ್ಲ, ಅದಕ್ಕೆ ಕ್ಷಮಿಸಿ ಅಂತ ಕೇಳ್ಕೊತೀನಿ ಸರ್. ಅವ್ರು ಬೇರೊಂದು ಕಾರ್ಯಕ್ರಮ ಇದ್ರಿಂದ ಅವ್ರು ಅದರಲ್ಲಿ ಇನ್ವಾಲ್ವ್ ಆಗಿದ್ದಾರೆ ಸರ್. ಸೊ ನನ್ನ ಸೇರಿದಂತ ಎಲ್ಲ ನನ್ನ ವಿದ್ಯಾರ್ಥಿ ಮಿತ್ರರಿಗೂ ಹಾಗೂ ನನ್ನ ಸಿಬ್ಬಂದಿ ವರ್ಗದವರಿಗೂ ಹಾಗೂ ಇದಕ್ಕೆ ಶ್ರಮಿಸುತ್ತಿರುವ ನನ್ನ ಕಾರ್ಯ ತಾಂತ್ರಿಕ ಸಿಬ್ಬಂದಿಗಳಿಗೂ ಕೂಡ ಅಕಾಡೆಮಿ ವತಿಯಿಂದ ಮತ್ತು ವೈಯಕ್ತಿಕವಾಗಿ ಧನ್ಯವಾದಗಳು. ಥ್ಯಾಂಕ್ ಯು ಸರ್. ವಿದ್ಯಾರ್ಥಿಗಳಿಗೆ ಒಂದು ಸೂಚನೆ. ನಾಳಿನ ಉಪನ್ಯಾಸ ಕಾರ್ಯಕ್ರಮದಲ್ಲಿ ಹಾವುಗಳ ಪ್ರಪಂಚದೆಡೆಗೆ ಎಂಬ ಉಪನ್ಯಾಸ ಮಾಲಿಕೆಯನ್ನು ಡಾಕ್ಟರ್ ಪ್ರಹ್ಲಾದ್ ಸರ್ ಅವರು ಸಂಜೆ 4 ಗಂಟೆಗೆ ಉಪನ್ಯಾಸ ನೀಡಲಿದ್ದಾರೆ. ಸೊ ವಿದ್ಯಾರ್ಥಿಗಳು ಹೆಚ್ಚಿನ ಸಂಖ್ಯೆಯಲ್ಲಿ ಹಾಜರಾಗಬೇಕೆಂದು ನಮ್ಮ ವಿಜ್ಞಾನ ಮತ್ತು ತಂತ್ರಜ್ಞಾನ ಅಕಾಡೆಮಿ ವತಿಯಿಂದ ತಿಳಿಸುತ್ತಿದ್ದೇವೆ. ಹಾಗೂ ಯಾವುದೇ ರಿಸೋರ್ಸ್ ಪರ್ಸನ್ಸ್ ಅಂದ್ರೆ ಸಂಪನ್ಮೂಲ ವ್ಯಕ್ತಿಗಳು ಕೊಡ್ತಾ ಇರತಕ್ಕಂತ ಪ್ರಶ್ನೆಗಳಿಗೆ ಮಕ್ಕಳು ಹೆಚ್ಚಿನ ಸಂಖ್ಯೆಯಲ್ಲಿ ಉತ್ತರಗಳನ್ನು ಬರೆದು ಕಳುಹಿಸಿ ಇಟ್ಟಿರ್ತಕ್ಕಂತ ಒಂದು ಕ್ಯಾಶ್ ಪ್ರೈಸ್ ಅನ್ನು ತಮ್ಮ ಕಿಸೆಗೆ ಹಾಕಿಕೊಳ್ಳಬೇಕೆಂದು ಮತ್ತೊಮ್ಮೆ ತಿಳಿಸುತ್ತಾ ನಾಳಿನ ಉಪನ್ಯಾಸ ಕಾರ್ಯಕ್ರಮದಲ್ಲಿ ಎಲ್ಲರೂ ಭಾಗಿಯಾಗಬೇಕೆಂದು ತಿಳಿಸುತ್ತಿದ್ದೇನೆ. ಥ್ಯಾಂಕ್ ಯು ಸರ್.